Rotary drilling involves a lot of equipment, people, and special materials. One material vital to rotary drilling is drilling fluid, called mud by those familiar with it. This is some of the equipment used to test drilling mud in the field. Tests are made to check on the properties of the mud and to ensure that the mud is performing as desired. The API Standard Mud Report form is used to record the results of the tests. The form tells rig personnel what has been done to the mud and provides a written record of the well's history. The form provides, starting at left, spaces for the name and address of the operator and for the well's name and number. Moving to the right, the drilling contractor's name and address is filled in, and the field or block number, as well as the county or parish in which the well is located. At far right is the rig number, spud date of the well, and the state or province. Also filled in is the rig's operation, including its present activity, bit size and number, drill pipe size and type, and the drill collar size and length. Casing size and length is entered along with mud type. Also written in is the mud volume in the hole, pits, and total volume. Circulation data includes pump size and make, barrels per stroke, strokes per minute, barrels per minute, annular velocities opposite the drill pipe and collars, circulation pressure, and the times required to circulate bottoms up and all the way around. Here is recorded the size and hours of use per tower the mud conditioning equipment has received. In this case, a size 12 desander has received 7 hours of use, and a size 4 desilter has received 7 hours of use. At bottom, the mud properties specifications are entered, showing a required mud weight of 9.5 pounds per gallon, a funnel viscosity of 60 seconds per quart, and 5 to 10 milliliters, ml, of filtrate. We'll see what these figures mean as we go along. And in this part, test information on the mud properties is written in. Let's go over some of the common tests. First, the mud man gets a mud sample from the mud return line and takes its temperature. Temperature affects the mud's characteristics. He writes it down on the form. In this case, it's 110 degrees Fahrenheit. Also, he records the time, 0800, or 8 o'clock in the morning, and the depth of the well, 10,580 feet. Next, the mudman weighs the mud in a mud balance. Weight may be in pounds per gallon, pounds per cubic foot, or kilograms per liter. Mud weight is important because it keeps formation pressure in check and affects the drilling rate. The mudman records the weight, in this case 9.5 pounds per gallon. Also, he writes down the mud gradient, 0.495 pounds per square inch per foot of depth. The mud gradient is the amount of pressure the mud exerts at different depths in the hole. The mud gradient in psi per foot is equal to 0.052 times the mud weight in pounds per gallon. In this case, the gradient equals 0.052 times 9.5, which equals 0.495 psi per foot. Next, the mudman measures the mud's resistance to flow, its viscosity, with a marsh funnel. He pours 1,500 milliliters, about a quart and a half, of mud into the funnel and times the number of seconds it takes for exactly 1 quart of mud to flow out of the funnel. We need to know the mud's viscosity because viscosity determines how easy or hard it is to pump the mud. He records the funnel or apparent viscosity and the temperature of the mud, in this case 60 seconds per quart, and 110 degrees on the form. Then, to obtain a more scientific measure of the mud's viscosity, the mudman uses this instrument. It's called a rheometer, a rotational viscometer, or a VG meter. It may be hand-cranked, as this one is, or may have a motor. In any case, a viscometer measures the mud's viscosity in terms of centipoises. A centipoise is a unit of measure for viscosity, just as an inch is a unit of measure for length. To use the viscometer, fill a container with mud and place it exactly to the scribe line on the rotor sleeve. On a motor-driven viscometer, push this button down so the rotor turns at 600 revolutions per minute, or RPM. Turn the instrument on and wait for the dial reading to reach a steady value. In this case, it is 60. Now pull the button up so that the rotor turns at 300 RPM. Again, wait for the dial reading to come to a steady value. In this example, it reads 50. The plastic viscosity of the mud in centipoises is obtained by subtracting the 300 RPM reading from the 600 RPM reading. So in this instance, 60 minus 50 equals 10 centipoises. The plastic viscosity of 10 centipoises, CPS, is recorded on the form. The yield point of the mud, a measure of the electrochemical forces causing resistance to flow, is determined by subtracting the plastic viscosity, in this case 50. Thus 50 minus 10 equals 40. The figure of 40 is written on the form. Notice that yield point is in terms of pounds per 100 square feet and not in centipoises, as is plastic viscosity. Both yield point and plastic viscosity are useful in determining mud treatments and in making certain calculations used in drilling fluid engineering. Next step is to determine the mud's gel strength. Gel strength is a measure of the mud's ability to temporarily solidify, or gel, when it is not flowing. There are two gel strength measurements to take. First is the initial gel strength, the mud's gel strength before it has a chance to gel. Let the mud sample rest for 10 seconds. Then slowly and steadily turn the wheel on the VG meter by hand counterclockwise to produce a positive reading on the dial at the tip of the man's thumb. The maximum reading obtained is the initial gel strength in pounds per 100 square feet. The figure, in this case 4 pounds per 100 square feet, is recorded on the form. The second gel strength measurement is the 10-minute gel strength. To determine it, restir the mud at 600 RPM for 10 seconds, then shut off the viscometer and let the mud sit still for 10 minutes. The 10-minute wait gives the mud a chance to gel, and the test reveals the amount of force needed to start the gelled mud flowing. After the 10-minute wait, turn the hand wheel counterclockwise and obtain the maximum dial reading. The 10-minute gel strength is also in terms of pounds per 100 square feet. Here it is 15 pounds per 100 square feet. By using hydrian paper, litmus paper, or a pH meter, the next thing the mudman determines is how acid or how alkaline the mud is in terms of pH. Almost all mud should be alkaline. That is, the pH reading should be above 7 in order to minimize drill pipe corrosion and maintain the mud stability. This mud's pH is 9.5. This equipment is used to determine the mud's API filtration rate. The mud sample is placed in the white container and is put under 100 pounds per square inch of pressure for 30 minutes. The liquid part of the mud, the filtrate, runs into the graduated cylinder below the white container. Filtration rate gives an indication of the amount of filtrate lost to downhole formations and the amount of solids or wall cake build up on the wall of the hole. The amount of filtrate in milliliters is noted and is recorded on the form. In this case, it is 9.0 milliliters per 30 minutes. Then the solid part of the mud, the wall cake, is removed from the filtration container and its texture is noted. Also, the thickness of the cake is measured and recorded on the form in 30/32 of an inch. Here the thickness is 3/32. Here a mud engineer is measuring the effect of increased temperature and pressure on the filtration rate. This test is called the API High Pressure High Temperature HPHT filtrate test. It is run only occasionally. However, there is space provided on the form, and if run, the pressure and temperature at which the test was made should be entered, as well as the amount of filtrate obtained. Using the filtrate obtained from the test and a sample of the mud itself, several chemical tests are made. The first chemical test, especially with lime muds with a large amount of calcium, requires that 1 milliliter of mud be mixed with pure distilled water. This is used to determine what is known as the phenolphthalein endpoint. Phenolphthalein endpoint is a very accurate measure of the mud's alkalinity. Phenolphthalein is an indicator solution which, when added to the mud sample, turns the sample purple or wine-colored if the pH of the mud is above 8.3. Then a 0.1 normal or a 0.02 normal solution of sulfuric or nitric acid is added to the colored mud sample with a pipette. Normal refers to the strength or concentration of the acid solution. The sulfuric or nitric acid solution is added until the color of the mud sample changes back to its original color. The number of milliliters of acid that it took to change the color back is noted and is recorded on the form where it says alkalinity mud PM. PM is the abbreviation for the phenolphthalein endpoint of the mud. Here it is 0.3. A similar test is run on the filtrate sample to determine its alkalinity. 1 milliliter of filtrate is added to the container or casserole along with distilled water. When phenolphthalein is added, and if the pH is above 8.3, the filtrate sample turns purple. Then 0.02 normal sulfuric acid is added with a pipette until the color just disappears. By the way, this operation is called titration. The amount of acid it took to make the color disappear is recorded on the form as the phenolphthalein endpoint of the filtrate, abbreviated as PF. Here it is 0.3. Another test made on the filtrate is the chloride test, which measures how salty the mud is. Adding a few drops of potassium chromate turns the filtrate sample yellow if salt or chloride is present. This test is useful to determine if salt formations are being drilled or if saltwater flow has been encountered. Then a 0.282 or a 0.0282 normal silver nitrate solution is added with a pipette until an orange-red color persists for about 30 seconds. The amount of silver nitrate added is noted, a few calculations are made, and the amount of chloride in parts per million, ppm, is written on the form, 1,000 in this example. For the next test, 1 milliliter of filtrate is added to a casserole and distilled water is mixed in. This is used to determine the hardness or amount of calcium or magnesium in the mud. Calcium-bearing formations are frequently drilled, which causes the amount of calcium to increase and upset mud properties. A strong buffer, a chemical that neutralizes both acids and alkalis, and a hardness indicator called calgamite is added to the filtrate sample. The color changes to wine red if calcium or magnesium is present. Next, a solution called standard versinate is added until the color changes to blue. The number of milliliters of versinate added is noted. Total hardness is the milliliters of versinate added times 1,000. Parts per million calcium is the total hardness times 0.4. For example, if 0.1 milliliters of versinate were added, then 0.1 times 1,000 equals 100. 100 times 0.4 equals 40 parts per million calcium. Another test is a measurement of the percent by volume of sand in the mud. Sand is abrasive and causes erosion of metal and rubber parts of the rig. It is important to keep the sand content at a low level at all times. First, a sample of mud is poured into a special tube to the level where it says mud to here. Water is added to the mud and the tube shaken to mix the water and mud together. Next, the sample is poured into this cylinder that has a 200 mesh screen in it. The screen traps any sand in the mud. Several washes of the tube are made to make sure all of the sand gets out of the tube and onto the screen. The orange screen container is placed in a funnel with the sand on the screen pointing down. The end of the funnel goes into the tube. The sand on the screen is washed down into the tube with water. The sand is allowed to settle in the tube, and the percent by volume of sand is read directly from the tube. This is a mud still or distillation unit. It is used to determine the percent by volume of solids, water, and oil in the mud. It evaporates the liquid part of the mud, leaving behind a residue of solids. All muds operate at an optimum solids concentration for a particular mud weight. For this reason, determination of the amount of solids is one of the most important checks a mud engineer makes. The liquids are condensed into a graduated cylinder, and the percent by volume of oil and water is calculated. Then the amount of calcium in parts per million, 40 in this case, the sand content, 2%, the solids content, 5%, the oil content, 2%, and the water content, 93%, are all entered on the report form. Many additional tests may be run. For instance, this is methylene blue test paper. It is used to measure the amount of drilled solids and the bentonite clay content of the mud by comparing a number of tests with the sample at bottom. Also, the amount of preservative, usually formaldehyde, in the mud can be determined using a test similar to the one for determining the phenolphthalein endpoint. Likewise, the sulfate and sulfide contents can be measured using barium chloride. And since drill pipe corrosion is a problem with some muds, these corrosion rings can be placed in the drill string. After a given amount of time has passed, the rings are removed from the string and the corrosion rate measured. After the mud is tested, the engineer recommends any treatment that may be necessary on the form. Here, 10 sacks of bentonite, called Magcobar by this mud company, 10 sacks of lignosulfonate, called spursine, and 2 sacks of caustic soda should be added. Also, the engineer records what was happening while he was testing the mud. In this case, the rig was drilling ahead at 10,580 feet and experienced a tight spot in the hole at 10,400 feet. Finally, a cost-time summary may be made on the basis of the amount and costs of products added to the mud system per 24 hours. and bit information is entered, including the bit type, jet sizes, weight being run on it, and the RPM rate. When filled out in detail, the mud report form provides a good history of the well. When examined by the operator, it is often possible that the information will allow future wells to be drilled more economically and safer.